Hello, I welcome you all in this course on power plant engineering. Today we will solve a few numericals to have clear insight of the phenomena, whatever I have told you or whatever I have explained you in the previous lectures. So today we will be solving some numericals based on the theory which I have explained you earlier. Now numerical number 1, it is based on the Rankine cycle. So in a Rankine cycle, steam enters the turbine at 140 bar and 550 degrees centigrade. So obviously this steam is superheated steam. If the exhaust pressure is 0.06 bar or 6 kilopascal, so the vacuum order of the vacuum is very high, and all processes are reversible, it is an ideal cycle. Find the cycle thermal efficiency, work ratio and steam rate. Then there is another part, if the efficiency of the turbine is 80%, so this is not an ideal case, this is the case where efficiency of the turbine is 80% and the efficiency of the pump is only 50%. What is the thermal efficiency in this case? Now third one is, with this value of turbine and pump efficiency, if the boiler efficiency is also 85%, calculate the fuel rate required in kg per kg of steam if calorific value of the fuel is 42 megajoules per kg. So 42 megajoules per kg is typically the calorific value of diesel. So it is, the boiler is oil based, the furnace oil based boiler. We will start with this. So first of all, we will draw the Rankine cycle, ideal Rankine cycle, or here in this Rankine cycle, the steam is obviously superheated. If you look at the steam table at this pressure of 140 bar and 550 degrees centigrade, you will find that the steam is superheated. So if you draw the Rankine cycle on temperature entropy diagram, this is x is equal to 1, the diagram is going to be like this. So 1, 2, 3, 4 and this is 5, and the direction of the process is like this. Now first of all, we will calculate, because we need, for in order to find the output of the turbine, we need H1 minus H2. Now H1 we can comfortably take from the steam table. If we look at the steam table at 140 bar, 140 bar and 550 degrees centigrade temperature, in that case you will get 3967.5 kilojoules per kg. This is the value of H1. Now we have to find the value of H2, and we do not know the quality of steam at state 2, right? But one thing we know for sure, that entropy at state 1 is equal to entropy at state 2. So what we are going to do, we will take entropy at state 1 can be calculated, can be taken from the steam table because it is superheated steam. So if you go to the superheated zone properties of steam, you will find the entropy of the steam at state 1. So entropy of the steam at state 1 is 7.116 kilojoules per kg Kelvin. That is entropy of the state. But what about entropy of state 2? State 2 quality we do not know, right? But entropy of state 2 is known to us. So S1 is equal to S2F. It means entropy of at this pressure 0.06 bar of liquid plus XSFG of state 2, right, or at this pressure 0.06. So for 0.60 bar at saturated properties, we look for the entropy of the liquid and the entropy of the saturated vapor, or change in the entropy from liquid to saturated vapor. So these values we have taken from steam table, and they are coming as 0.5209 kilojoules per kg Kelvin plus X 7.8103 kilojoules per kg. Now from this, because this is equal to S1 is 7.116. 7.116 is equal to 0.5209. This is entropy of the liquid at 0.06 and multiplied by the quality of vapor and change in entropy from liquid to vapor phase. From here we get the value of X as 0.844. right? This is the quality of vapor at state 2. We have properties of energy also, means enthalpy of liquid at this pressure 0.06 pressure, enthalpy of saturated wet vapor also we have 0.06 bar pressure, and latent heat is also known, that can be taken from the steam table. So, at S3 or enthalpy of the liquid at this pressure, that is S3, it is 151 kilojoules per kg, and this is not H, this is H3, not S3, it is H3 enthalpy at 3, and latent heat HFG at 3 is 2416 kilojoules per kg. Now, using these values, we can find the value of H2 as 151 plus 0.844 multiplied by 2416, and there we get the value of H2 as 2190.1 kilojoules per kg. So, now we have the value of H1 and we have value of H2. So, steam turbine is an open type of system, right? If you apply first law of thermodynamics, you will find that the output of the turbine is H1 minus H2, that is H1 minus H2, that is the output of the turbine. Now, part of the output of the turbine is also used for pumping the liquid at state 3 to state 4, or in increasing the pressure of condensate. Now, part of that work has been used. So, work of the pump is specific volume at state 3 VdP delta P, and delta P is P4 minus P3, right? And if you look at the work of the pump is equal to specific volume at 3 is 0.01. So, it is 0.001 meter cube per kg. It is taken from the steam table. P4 is 140, this is 0.06. They are in bar. So, it is converted into the kilopascal, so that we get output in kilowatts. Uniformity of the unit has to be maintained. So, it is coming is equal to 13.994 kilojoules per kg. This is the work of the pump. Now, this is the output. Work of the turbine is 3967.5 minus 2190.1, and if we take difference of these two, then we get 1777.4 kilojoules per kg. Now, this turbine, a part of this turbine output is used for the pumping. So, net output is difference of these two, and then we have to find the efficiency of the thermal efficiency of the plant. So, thermal efficiency of the plant is net output, that is 1777.4 minus 13.994 divided by net heat supplied in the cycle. Net heat supplied in the cycle is H1 minus H4. H1 is with us, H1 minus H4. H1 with us, H3 is with us, but H4 is not with us, right? So, in order to find H1 minus H4, we will take H1 minus H3 plus work of the pump. Sorry, this not plus, this is minus, not plus, this is minus, right? So, this minus pump work. So, this will give us the value as 3967.5, and H3 is 151 minus pump work is 13.994, because as the point is shifted from 3 to 4, the heat added in the boiler is reduced, right. So, pump work on the one side, the high grade energy is being used for increasing the pressure. On the same side, it has reduced the requirement of low grade energy. So, if we solve this, we get the thermal efficiency of the order of 46.37%. this multiplied by 100. So, we will get 46.37%. Another term is work ratio. Now, the work ratio is the net work divided by the work output of the turbine. Now, let us understand what is the meaning and what is the significance of work ratio. Thermal efficiency is okay. 46.37% of low grade energy has been converted into the high grade energy. This is the net output. This is the efficiency of the cycle. Now, when we talk about the work ratio says net output divided by the output of the turbine. So, here the net output is 177.4 minus 13.999. Right. So, net output is, if we want to have work ratio, that net output is 1763.4 and turbine output is 1777.4. It is 99.2%. It is quite high. Now, concept of work ratio has come into the picture. If you look at the Carnot cycle has very high efficiency, but at the same time it has very low work ratio. If you look at the Carnot cycle, right, this is the turbine work and this is the work of the pump. The work of the pump is also quite significant. So, efficiency is high, no doubt. Carnot cycle efficiency is high. At the same time, it has got very low work ratio, and it means for Carnot cycle, suppose I need an engine which is working on Otto cycle or Rankine cycle. The size may be this much for 1 kilowatt engine. For Carnot cycle based engine, size will be this much, because work ratio is low. When the work ratio device is low, the size of the device will increase for the net output. So, next part of this is, if the efficiency of the pump is 50%, and turbine efficiency is 80%. So, if we draw a temperature entropy diagram here again, temperature entropy diagram here again. Right, so 1, 2, 3, 4, 5. Right. Now, turbine efficiency is 80%. So, no longer it is a vertical line. So, it is 80%. So, this is 2 dash. And at the same time, pump also is not a vertical, it is 4 dash here. So, if the efficiency of the pump is less amount of heat will be added in the boiler. At the same time, if the turbine efficiency is 80%, the output also be less from the turbine. So, now we will take this into the account. And before going for this, there was one thing more, specific steam consumption. So, steam in previous part, so specific steam consumption is 3600 divided by net work output, and this will give 3600. Net output was 1763.4 is equal to 2.0415 kg per kg per kilowatt hour. That is the specific steam consumption. That was requirement of the part A. Now, in part B, the pump efficiency is 50%. It means 0.5 is equal to H4 minus H3 divided by H4 dash minus H3. Now, here H4 minus H3 is known to us, that is 13.994. H4 dash is not known to us, H4 dash, and H3 is also known to us, that is 150. Right, and from this we can get the value of H4 dash, and H4 dash value is H4 dash, or we can take this H4 dash, this is H3, So simply H4 dash minus H3 we can get from here, that is 13.994 divided by 0.5, because we will always be using this H4 dash minus H3. So it is coming around 27.998 kilowatt. Sorry, kilojoules per kg, not kilowatt. Mass flow rate is not given. So it is going to be kilojoules per kg. Kilojoules per kg. Okay. So now the pump which was consuming 13.994 kilojoules per kg, now it is consuming just double of the power, 27.998. Regarding turbine, efficiency of the turbine is again H1 minus H2 dash divided by H1 minus H2. Now H1 minus H2 is already with us, so H1 minus H2 dash is going to be 1421.92 kilojoules per kg, because H1 minus H2 dash is known and this is equal to 0.8, right. So H1 minus H2, sorry, this is H2 dash, H1 minus H2, H1 minus H2, you are right, पहले सही था ना, पहले सही था ना, हाँ, H1 minus H2 dash, it is H1 minus H2 dash divided by H1 minus H2. So from here we will get the H1 minus H2 dash, definitely it is going to be less than H1 minus H2 and it is going to be 1421.92 kilojoules per kg. Now thermal efficiency again. Now we are calculating again thermal efficiency. Now we will take H1 minus H2 dash minus pump work, that is 27.998, now divided by again H1 minus H3, this is H1 minus H3, these values are with us, minus work of the pump. Now this is due work of the pump, that is 27.998 kilojoules per kg. H1 minus H3 we have already calculated, right, and this will give us the thermal efficiency. If you calculate the thermal efficiency out of this, it is going to be 36.79%. So because ideal cycle had efficiency approximately 46%, but because now the real cycle, the efficiency of the turbine, we have taken only 80%, we have taken efficiency of the pump only 50%, so pump is consuming double of the power. Now here the efficiency has reduced to 36.79%. Now efficiency of the boiler has to be considered now. Now efficiency of the boiler in the last part is 85%, right. Now 85% means 0.85 is equal to H1 minus H4 dash. So H1 minus H4 dash is means 3967.5 minus 164.994 divided by mass of the fuel and calorific value of the fuel. Now 39675 we have taken enthalpy at state 1. We have taken enthalpy at stage 4 dash. How we have done? We have just taken enthalpy at stage 3, enthalpy at stage 3, and pump work is added. So pump work is when you add the pump work, you get the enthalpy of stage 4, right? And mass of the fuel burned and the calorific value of the fuel. Calorific value of the fuel is known to us, that is 42,000 kilojoules per kg. From here, unknown is mass of the fuel. So mass of the fuel burned can be taken here and it is 0.10059 kilojoules per kg. Now this is the answer. This is the amount of fuel which is burning for. This is the amount of fuel which is burning for. So mass of the fuel is 0.010059 kg per second, right? So after this, we'll take another numerical, which is the next numerical is related with the boiler, use of economizer in the boiler. Calculate the percentage of fuel saving by installation of an economizer with Lancashire boiler if steam leaves boiler dry and saturated. So now in numerical 2, it is calculate the percentage of fuel saving by installation of an economizer with Lancashire boiler if steam leaves the boiler dry and saturated at 13 bar pressure. The feed water enters the economizer at 40 degrees centigrade and leaves 125 degrees centigrade. Now, the position of, if you remember the position of economizer is that it comes into the contact with the flue gases. When the flue gases are leaving the boiler, then economizer is fixed. So, feed water which is going to the boiler is heated in the economizer. So, feed water earlier which was going in the boiler at 40 degrees centigrade, now it will be going at 125 degrees centigrade, and that is going to be the saving in energy in the boiler. So, we will start with the enthalpy of steam at 13 bar. Enthalpy of steam at 13 bar. So, that we can take from steam table, that is 2785.7 kilojoules per kg. So, this is the amount of steam, saturated steam, the enthalpy of saturated steam at 13 bar. Now, we are applying the economizer. In economizer, the sensible heating taking place, the sensible heating of is taking place, and the water is getting heat, the feed water is getting heated up. So, sensible heating is mCp delta T, right? We are taking 1 kg of water, we are analyzing for 1 kg of water. So, mass flow rate, let us say, is 1 kg, or let us say 1 kg of water, mass flow rate is 1 kg, Cp is 4.18 and delta T is 125 minus 40, right, and this will give the value 5355.3 kilojoules kilowatts, or agar mass flow rate is 1 kg per second. If we take 1 kg of water, then it is kilojoules per kg. We are taking 1 kg of water. Or if mass flow rate is 1 kg per second, then it will be 1 kilowatt. So, Q is 355 per kg of water is 355.3 kilojoules per kg. Now, right? Now, how much heat is reduced? How much heat is, because H water is 355.3, right? Initially it was required 2785.7. Now this will be reduced from this, right? So net saving will be 355, it is saving, divided by 2430.4. Now solve a numerical. Purpose of economizer boiler, because economizer is provided, it is installed in the exhaust side of the boiler where the flue gases come into the contact with the economizer, and this economizer takes heat from the, it is a sort of heat exchanger where transmission of heat takes place from the flue gases to the feed water, and that feed water, this heated feed water is supplied to the boiler. So initially here when the boiler, if I will read out the numerical, calculate the percentage of fuel saving by installation of an economizer with Lancashire boiler if the steam leaves the boiler dry and saturated at 13 bar. The feed water enters the economizer at 40 degrees centigrade and leaves at 125 degrees centigrade, right. So now in this case, I have given you the physical values, and this numerical you can solve by yourself, right. First of all, calculate the enthalpy at enthalpy initially without economizer. So enthalpy, first of all, calculate enthalpy at 13 bar, enthalpy of saturated vapor at 13 bar, right. Enthalpy of liquid which is entering the boiler at is 40 degrees centigrade. So at 40 degrees centigrade, enthalpy of the fluid, 14 degrees centigrade saturation temperature, enthalpy of the liquid, enthalpy of vapor at saturated vapor at 13 bar. If you calculate these two and take the difference, that is the actual amount of heat which is being added in the boiler. If you look at the Rankine cycle, so 1, 2, 3, 4. So 2 to 3 and 3 to 4. 2 to 3 and 3 to 4. This part is this energy addition is taking inside the boiler, right? Here we are neglecting the pump work because pump work is not mentioned. So, we will say that starting from 1 to 3, starting from 1 to 3 and 3 to 4. So, heating is taking place, sensible heating from 1 to 3 and then 3 to 4. In this case, pump work is neglected. So, we can take enthalpy at 4, that is enthalpy at saturated vapor at 13 bar, enthalpy at 1, it means at 40 degree centigrade, enthalpy of the liquid. So, that is the amount of heat which is being added. Now, we have put an economizer. So, this economizer, what it is going to do? It will add some heat, sensible heat to the feed water, and that is going to be for 1 kg of water, it is going to be m Cp delta T. So, 4.18 delta T is 125 minus 40. Now, this heat addition will shift 0.1 to 0.1 dash, and now actual amount of heat which is to be added is from state H4 to H1. H4 minus H1 dash, H4 minus H1 dash. This is the actual amount heat which is going to be added in the case of economizer, and when you will solve the numerical, you will find that there is a 10 to 15% saving in heat in the boiler. So, 10 to 15% saving is a quite significant saving. So, these accessories which are used in the boilers, whether it is a superheater or an economizer or air preheater, these accessories definitely improves the efficiency of the system. So, now after numerical 2, we will solve another numerical, this is the last one. Following observations were taken during a test of a steam boiler. So, steam pressure 900 kilopascal gauge. So, atmospheric pressure has to be added before doing any calculation. Quality of steam 0.96. So, if you look at the Rankine cycle again, here it is not fully saturated, it is 0.96, right. Quantity of feed water is 680 kg per hour. Temperature of feed water is 26 degrees centigrade, this is normal water which is fed to the boiler. Coal is 80 kg per hour, this is the amount of coal which is being used. And calorific value of the coal is 29274 kilojoules per kg. Quantity of ash collected is 8 kg per hour. Then CV of ash and unburnt coal is calorific value is also given here. Mean specific heat of flue gases is given 1024.5 kilojoules per kg Kelvin. Mass of the flue gases 18 kg per hour. Discharge flue gases temperature 330 degrees centigrade. Boiler house temperature 26 degrees centigrade. Perhaps at the same temperature the water is supplied. Atmospheric pressure 100 kilopascal. So, 9 kilopascal gauge. So, absolute pressure is 10 bar, 1000 kilopascal. And then we have to calculate boiler efficiency, percentage of heat loss to flue gases, percentage of heat loss to ashes. And so, it is a sort of preparation of the balance sheet of a boiler. A balance sheet of a boiler is also prepared, right. So, say fuel is burned in the boiler, that is 100%. That what part of the fuel is this heat released by burning fuel, is this heat is used for converting water into the steam, that is useful, meaningful use of the heat, because boiler is for that purpose only. How much heat is going out with the flue gases, how much heat is dissipated to the surroundings or going with the ash or the unburnt fuel. So, all this balance sheet has to be prepared for each boiler. It is a part of the boiler trial. So, we will start with the efficiency of the boiler. So, efficiency of the boiler is enthalpy or heat added to the water divided by amount of the coal burned. So, it is HF plus XHFG divided by calorific value of the coal, mass of the fuel burned multiplied by mass, right. So, it is HF is 762. I have taken these values from the steam table, plus quality of the steam, it is given 0.96 into 2013.6 minus 148.95. This is the pump work. Pump work has to be calculated. Okay. Pump work has to be calculated. Then not pump work. This is enthalpy of water. Sorry, not pump work. This is enthalpy of water. This is enthalpy of steam. This is enthalpy of water. So the change in a difference in enthalpy has to be taken, right? So this is the enthalpy of steam which is coming out of the boiler, and this is enthalpy of water which is supplied to the boiler. So, in order to find the net amount of heat added, difference of these two enthalpy has to be taken, and this is multiplied by 680, amount of steam generated. Calorific value is 29274 into amount of coal burned is 80 kg per hour. If you look at the values, so quantity of feed water is 680. So that is why I have multiplied there by 680. Coal used is 80 kg per hour. So that is why I have divided there by 680 kg, 680 and 80, right? And this will give the efficiency of the boiler. And once we have the efficiency of the boiler, and that is coming around multiplied by 100, and that is 75.1%. This is the efficiency of the boiler. Now the second part is heat carried away by the flue gases. Now in order to find heat carried away by the flue gases, that is Qg is equal to mass of the gas, Cp of the gas, Tg minus Tr. So mass of the gas is 18, if you remember it is 18, Cp is 1.0245. I have taken in kilojoules per kg Kelvin. In data it is given joules per kg Kelvin. I have taken kilojoules per kg Kelvin. Gas temperature is 330 and water temperature is 26 degrees centigrade, or the air temperature or the room temperature is 26 degrees centigrade. So air temperature is 26 degrees centigrade. Flue gases temperature is, because air is taken from the room. The room temperature is 26 degrees centigrade. That is why I have taken this as 26, and this gives the value 5606 kilojoules per kg. This is amount of heat which is carried away by the flue gases by burning 1 kg of coal. So therefore percentage loss, if we look at the percentage loss is 5606 divided by the calorific value. Calorific value is 29274 multiplied by 100. So percentage of heat which is going with the flue gases is 19.15%. Okay. So this is the amount of flue gases this is the amount of heat which is going away with the flue gases. Now mass of the ash, if you remember, it is 8 kg per hour. This is the amount of ash which is being generated during the operation of the boiler. Therefore percentage of heat, because calorific value of ash is given. Calorific value of ash is given 2802 kilojoules per kg, and mass of the ash is 8 kg per hour, right? So heat is going to be, the heat going with the ash is 8 into 2802 divided by 80 into 29274, because 80 kg of fuel is burned per hour, and this will multiply this by 100, this will give 0.957%. So 0.957, approximately 1% of heat which is generated is going with the ash. It is taken away by the ash. So total account of heat, if you take the total account of heat, so total efficiency is 75.1. So 75.1 is used for converting water into the steam. 19.15% of heat is going out with the flue gases. 0.957% of heat is going with the ash, right? If you take sum of this, this is going to be 95.207 or 95.2%. So percentage of unaccounted heat. So percentage of unaccounted heat is 100 minus 95.2, and it is going to be 4.7 or 4.8%. So 4.8% of heat is unaccounted. It is okay. I mean, in boilers, if the unaccounted heat is 4%, it is extra, because you cannot fully insulate the boiler. So some of the heat will be lost in the radiations, some through conduction heat transfer, radiation heat transfer, convection heat transfer, some heat loss has to be there. So this is the amount of unaccounted heat loss in a boiler. So today we have solved 3 numericals. We have done one numerical for, typical Rankine cycle. With ideal, we have taken one ideal case, one a real case. Then another numerical we solved for just to show the importance of economizer in a boiler, because economizer in a boiler can improve the efficiency significantly, save the energy and improve the efficiency of the boiler. And third one was about a sort of heat balance sheet of a boiler. That is all for today. Thank you very much.